Welcome to the second video in the series on rectangular coordinates and graphing of functions. Today I'm going to explain to you the complicated process by which your TI-89 titanium calculator graphs functions for you. It should be familiar to you. So here are the steps for plotting a function the way your calculator does it. First, we need a function to work with though, so let's find a function. Here is a simple linear function. I'm going to choose some values for x, and as I'm doing that, I'm going to go ahead and put them in this left-hand column. And these happen to be some of my favorite values to choose. They're usually pretty easy to use. Okay, so if I put -3 into the function f of x, but you know what? I'm going to plot this on a Cartesian plane, so I'm going to use the fact that plotting it on a Cartesian plane we usually call the dependent variable y. So if we put -3 in here, -3 times 2 is -6, minus 3 is -9. If I substitute -2, I get -4 minus 3 is -7, and so it continues. We now have a chart of our independent variable and the resulting dependent variable. So I will make some room to graph this. There is the point -3, 9. We can also plot 2, -7. We can plot -1, -5. We can go ahead and plot 0, -3. Let me make sure I have that one on there. 1, -1. And continue to 2, 1, and 3, 3. And then connect the dots. Because every point on that line between those integers also is a solution for that function. And that means that if you put one of these coordinate pairs into the function so that you're getting the function of 1, that should equal whatever the y value or the f of x value is. We should get -1 for that f of 1. 2 minus 3, yep, it is -1. It checks. Any point on that line will end with a true statement if you put the x and the y in position. This is actually the procedure your calculator uses to graph functions for you. I will show you how to do it specifically. Well, show you what you need to input to make your calculator do this in a couple days from now. For today, I want you to do this work on graph paper, which you may download from Blackboard. If you have a printer, we'll print it right out for you. If not, I hope you have collected some of your own. I think you are familiar enough with this process that we don't need the instructions, and let's make room and just start all over with a new function. So, since that was my first example of a function, this will be example 2 of a function that may be graphed by you. Okay, the function of x equals 1/3 x. So what are our x values and what are our y values that we will be graphing? And I say we because I do recommend that you follow along and take notes, and even pause and attempt this one yourself before I go on. If I jump in with my usual numbers, I'm going to get a lot of fractions returned as my dependent variable, my y value. And it's not impossible to graph, but integers sure are simpler when you're doing this by hand. So I'm going to choose multiples of 3, like -6. Why -6? Well, the function of -6 becomes this. I put -6 in for x because I'm multiplying by a fraction. I'm going to put it over 1. And I return the integer value -2. -3 produces -1. 0 is often very handy. In this case, it produces 0. 3 produces 1. And 6 produces a y value or a dependent value of 2. And this is what the function looks like if we graph it. So far, we have graphed 2 linear functions. Let's graph some nonlinear functions. let's look at the function f of x that is equal to negative x cubed. This function presents another example of why it's always a good idea in place of the x to place parentheses with nothing there yet. So we have negative x, or parentheses, cubed. And now I'm going to choose my x values. I'm going to start at negative 3. So when I put that negative 3 in there, negative 3 times negative 3 is positive 9 times negative 3 is negative 27. That's what I get for this much of the function. Negative 3 cubed is equal to negative 27. But I still have this negative from there. So this becomes a positive 27. Negative 3 returns the value of positive 27. Negative 2 returns the value of positive 8. Negative 1 returns positive 1. 0 returns 0. 1 returns negative 1. 2, negative 8. 3, negative 27. To make this graph a little bit easier to read, I have only marked every other value, so it's going by 2s, 2, 4, 6, 8, and even marking my units in 2s. This graph is already stretched off of the page. Graphing functions often makes it easier to understand what the domain and the range are. So what is the domain of this function? If you just analyze what negative x cubed could be, what could you put in for x and return a real number? Well, the answer is all real numbers. Let's use this vertical line to think about what's happening in the domain. Going out toward negative infinity. All right, this goes way off of our screen, but does it ever really stop heading toward negative infinity? No, it still keeps going that way. It just moves that way slower and slower by smaller and smaller amounts, but eventually it will get there. So it goes from negative infinity, goes all the way through 0, and goes slowly toward positive infinity, at least slowly relative to how fast it's going toward the infinities in the vertical directions. Because if we use a horizontal line to think about what's happening in the vertical directions, yeah, it's stretching from negative infinity down below our screen to positive infinity above our screen. So therefore the domain, or excuse me, the range is all real numbers. Okay, f of x can be any real number. Once again, I suggest you pause the video, try evaluating different values for this function, graph it, and state its domain and range, because that's what I'm about to do. Once again, we have a function for which it is a good idea to put in those parentheses for x, because inside those parentheses, I need to put a negative 2. And when I evaluate this, I get negative 2 squared is 4, negative 8 plus 4, or negative 4. So when we put the independent variable negative 2 into our function, it returns the dependent variable value of negative 4. Substituting some of my other favorite numbers for substitution. Here is the rest of my list and my graph. Let's talk about the domain and the range. Okay, we're going to remember that we're working with real numbers here. And yes, by the way, we will be graphing imaginary numbers at the end of the course. So let's take a look at what happens if you drag a vertical line from negative infinity to positive infinity. Is there any number, negative infinity to positive infinity, that x cannot be? And the answer is no. So actually I can get rid of that comma because all real numbers is the answer. That is the domain. So let's look at the range now. Does the range extend to negative infinity? Well, yeah, those arrows are pointing down to infinity. So it goes to negative infinity. Does it ever stop? Does it go to positive infinity? No. If you are inserting x values from negative infinity to positive infinity, that graph climbs up to the point where y is equal to 4, and it goes back down the other way. So the range in this case is all real numbers f of x, the y value, less than or equal to 4. Here we have an interesting function. Looks pretty simple at first, so let's just connect the dots. And we go through -2, 8, -1, 2, 0, 0, wait a minute, 0, 0, 1, 0. Now, if you remember the list of steps for plotting a function, we join our points with a smooth curve, but do I just go straight across? How do I make this smooth? Do I go straight across? Well, it's not advisable. It would be better to find another point in between those two. To do that, I need to expand our view here so we have some room to do this. I'm going to choose 1/2 because it's right between 0 and 1. Okay, if I go to 1/2, remember our original function was x squared minus x. So I'm going to put in 1/2 and 1/2 here, and I'm going to scoot this over for my next line so that I'm not running into that again, my y-axis. Okay, 1/2 squared is 1/4 minus 1/2. Well, I can rewrite 1/2 as 2/4. So I get -1/4. If I put in the independent value of 1/2 for x, I get out of that -1/4. And here is my point. All right, the question is then, is that the lowest point? Maybe we should try some other fractions. No, don't do that today. Don't go to that much trouble. I'm going to tell you that is the lowest point. I'm going to show you on your calculator later how it can figure that out for you. And when you get into calculus, you'll find some other ways to find out whether or not that's the lowest point. Okay, but for right now, we have found a point between 0 and 1. It is the lowest point because you gotta trust me. All right, so let's analyze this. The domain is all real numbers because although it goes up pretty steeply, it's still going out to negative and positive infinity as you move in either direction from 0. So it's all real numbers for the domain, and the range is all real numbers f of x greater than or equal to -1/4. Now, since we are doing this on the x and y coordinate axis, it is also fine if instead of writing it f of x, you choose to use the y greater than or equal to -1/4. And again, more examples. Here is a list of x and y values for the function f of x equals 1/x if we're graphing on an x and y axis. Now, we have looked at this function before. Here is the graph. Let's analyze it. The graph goes out toward negative infinity, so we can have infinitely negative x's. But as it approaches 0, we find that 0 gives us an undefined result. So 0 cannot be part of our domain. So it's all real numbers. X does not equal 0. And then in the y direction, if we're moving from negative infinity, which that arrow indicates it goes toward, and it goes up to positive infinity, but what happens right in the middle at 0? It never touches 0. So domain is all real numbers, x does not equal 0, range is all real numbers, f of x does not equal 0. Let's modify the function just a little bit, simply by adding 2 to the function. 1/x plus 2, it changes the domain and range of the graph. It's as if we have shifted the whole thing up 2, and the domain becomes all real numbers. X does not equal 0. That hasn't changed. But the range has. The range is now all real numbers. F of x does not equal 2. I think it's time for a piecewise function. All right, so we have f of x For the piecewise function, x plus 2 for x is greater than 1, and x squared minus 1 for x is less than or equal to 1. I made my t-tables, and I have graphed 4 points that are less than or equal to 1. And if I were to continue going toward the negative direction, this graph, which is a parabola, would continue as a parabola. It would continue in the negative x direction and in the positive y direction. But what happens at 1? At 1 for this piecewise function, the function value is 0. And that's because that's what is indicated here, less than or equal to 1. But then just after 1, anything greater than 1, we jump to this function. In order to indicate that, we actually do put 1 into this second part of the function and figure out what that value would be. It would be 3, but it cannot be that. Instead of putting a point at 1, 3, we leave an open circle, indicating it's not there, but it's infinitely close to that. What would the value be at 3.5? Well, it would be 7.5, which is 1, 2, 3, and 1/2. At 2, it is up at 4. 1, 2, 3, 4. And it continues in that fashion. So on this side of 1, the function looks like that. There's a piecewise function graph. Domain and range are as follows. All right, because the left side of our function continues to negative infinity in the x direction and positive infinity in the y, we can say the domain is all real numbers because even here at 1, there is a value. It is the value 1, 0. It is not what it would be if 1 were included in the second part of the function, but there is only one value at 1. That value is, if you put a 1 in, it has to go into x squared minus 1, which leaves you with the function value of 0. All right, so domain is all real numbers. However, range is limited. If we come up from negative infinity, the first place we hit the graph of the function is at 0, -1. So therefore, f of x has to be greater than or equal to -1. And then it continues to positive infinity. Now, there's something I hope you noticed as I went through all of these functions, and it has to do with this vertical line. For every case that I have written so far, I've told you it is a function, and it is. One of the ways you know it is a function is that each value on the x-axis, every one of these values has only one y value. So for every x, there's a unique y. For this x that I'm at right now, this is the y value, or the function's value. So if a graph passes the vertical line test, it is a vertical line, so that every x has only one y, then the graph is the graph of a function. Let's look at some more examples. Stubborn. So here we have the function where the function of x is y, and it is the square root of the quantity x plus 2. Notice the square root is there in the equation that you have been given. Therefore, it only means the positive square root, which is why only positive y values are graphed here. So this is a function. It will pass the vertical line test. That vertical line only hits the graph in one place for every x. What would something that's not a function look like? Well, it would look like this. So if we want to be consistent, we'll want to solve for y. Let's flip this first. Put y on the left. Don't always have to do that, but it's going to be a little bit easier to understand what I'm doing here. So y is on the left, we want to solve for y, so we are going to take the square root of both sides. And because I am taking the square root in the process of solving, it wasn't given to me originally. Now I have to say, okay, the square root of y squared is y, and I have to consider the positive and the negative square root of x. Once we have this graph, it's easy to see that for many x's, there are two values of y. All it takes is one x that has two values of y, and we can say that it is not a function. So just by looking at the accurate graph of an equation, you can determine whether or not it is the graph of a function. So is this a function or not a function? Does it pass the vertical line test? There are some asymptotes there where there are no y values. But yes, this is a function. For every x, there's only one y. It passes the vertical line test. The vertical line only crosses it in one place for each x. What about this one? Is this a function or not a function? Not a function. It's easy to see that at x equals 0, that graph crosses the y-axis in two places. All right, what about the next one? Is this not a function? Is it a function? Is it not? It is a function. And finally, function. No, yes, yes, no, no. It is not a function. This concludes our discussion of sections 3.3 and 3.4. Those deal with rectangular coordinates and graphing of functions. We also talked about the vertical line test and how given a graph or given an equation that you can graph, you can use a vertical line to tell whether that equation is a function or not. Happy graphing.